Well, it's good to be with you today. Just a little background. We manage all the computing resources for nuclear energy development at Idaho National Labs. We currently have quite a few users, and what my background is, I'm actually a mechanical engineer. I went to school, got a master's in design optimization, went out and worked for Pratt & Whitney for about 5 years, doing jet engine optimization. Later, Idaho National Labs knew that I knew how to use computers, and so they asked me to come out and help their engineers apply our HPC to the engineering challenges that we have at the Idaho National Lab. So is there a clicker that I can use to go through this? Is it up? Is this it? All right. Thank you. Yeah, we'll work on that for the next speaker. Anyways, a brief outline is we'll talk a little bit about the history of the Idaho National Lab HPC, and then that will help us understand, as we've grown, some of the job scheduling issues and resource issues that we've had. And then we'll talk about how we've done progression of troubleshooting with our user base. And then also, as we've grown, management wants more information, which I don't understand why, but they do. And then next we'll talk about how we use PBS hooks to meet some of these challenges and where we found a good fit for them, where we didn't quite find a good fit for them. And last we'll talk about the lessons learned. So anyways, back in 2004 we had about 500 cores. We had a big system called Ozone. It was in the top 500, but not very close to number one. And we had about 20 users, and we were using SGE for our job scheduler. In 2007, that's when I started. We just barely finished a procurement with SGI, and we bought ourselves a system called iStorm, which was one of the first systems, and it had 2,048 cores on it, and we had another smaller cluster, which is about 800 cores. So we're running about 3,000 cores, and we had about 40 users. And we were using 3 different schedulers. And then about 2011, we bought our newest system, which is called Fission. And that has 12,500 cores on it. And we've moved completely to PBS to manage our environment. But with these challenges, as technology's improved, computers have gone diskless. And that creates a whole new problem with scheduling jobs because of when you run out of memory, your machine dies. And we get grumpy users. I don't know if anybody else has dealt with grumpy users, but I do on a daily basis. Part of it also, as you can see, in 2007, when I started, we had 40 users, and now we have over 100 users every month running jobs. And we have over 300 users, and as our mission, we're trying to bring more and more users in to do nuclear research at our lab. And so we partner with different universities. The 3 in Idaho, we partner with them, some out of Wyoming, and we've even partnered with other national labs because our computers are set up to run nuclear codes instead of the big weather simulation codes at their lab. So yeah, that's been the challenge as we've grown. And our staff has remained about the same. We've kept about 10 user support and system admins for these years. And you can see we've gone over 30 times our resource growth. And so these are some of the common questions I get as a user support person. My job's not submitting or scheduling, why? And these are some of the messages they get. Job exceeds queue and or server resource limits. Now, I don't know if you know what that means, but most of my users who have never seen an HPC system have no clue what that means. And if we've learned that if our users have a negative experience, get frustrated, they'll get turned off and they'll go to their desktop and then they'll not take advantage of our resources. The next thing is my job is stuck in queue due to queue limits. It will submit the job, but it will not schedule. And they think everything's good because they got a job ID. The next thing is we try to show our users how loaded our systems are. But currently, some of the ways that PBS reports back doesn't really help them, and a queue stat doesn't help them see the actual true resources that are being consumed. And then the last thing is we have 4 different clusters, and they'll try to move scripts from one cluster to the next. And on one cluster, we have 8 cores. Another cluster, we have 12 cores. Another cluster, we have 24 cores. Another cluster, we have 32 cores. And so sometimes they get a little confused on which cluster they're on. Also, my job dies immediately, and why? Now, I've seen in the HPC Wire that Bright Computing calls it the black hole node. I know Cray, they have a node health check script out there to try to determine what's going on, but a lot of times as your clusters get bigger, one bad node causes a lot of frustration and headache for the rest of us. So we're trying to figure out how to resolve that. And also, some of the issues, though, is we share a lot of our systems with users. And so some user will go in and fill up temp and cause a problem for other users. Other times, I just get a message that says the node failed to join job. Now, as an administrator, that doesn't give me a lot of information besides it didn't join the job. And then also, sometimes our SSH connections get a little goofed up. So here's some of the examples of what our users see. This first one here, they'll submit a job, and if they do a Q sub minus capital I know it looks like an L, but I'll get my fonts working better next time, is they'll submit this job, and our system, Fission, has 32 cores, 64 gig of memory. But since it runs diskless, it's actually about 63 gigs of memory. And so our users don't quite understand that. And if they do a Q sub minus capital I, it'll just sit there and wait. It will not submit, and they'll just sit there and call me up an hour or two and say, why isn't my job submitting? And it's a memory violation. Second one, if they don't use a minus capital I, it rejects their job and says job exceeds queue resource and or server resource limits. Same problem, just a minus capital I, but one caused a lot more confusion, the other one causes confusion, and then they call me and say, why isn't it submitting? And we have to help them understand that our cluster is diskless. This next one is they'll submit a wall time to our workday queue, which only allows 8 hours of runtime. And they'll submit the wrong queue limits, and they'll get the job exceeds queue and or service resource limits. Still wondering why and what's the actual limit I got to schedule to. This one here, they'll schedule it, and on 3 of our systems it'll schedule, but it will never submit because they have it on the wrong cluster with 32 cores instead of the 24, 12, or 8. And this last one is they'll submit more cores than our queue actually allows, and it schedules and it just sits there. And they wonder, and they'll call me back after a weekend and say, hey, I put it in Friday night, why didn't it work? And then I have to explain to them, well, we only allow 512 cores to run over a week's period of time, more than a week, and you asked for a lot more than that. Doesn't work. So here's sort of my progression. In 2007, when I took over PBS, is when I'd wait for a call or an email when a job didn't submit, or I'd do a QStat minus F and just see, or QStat and see what jobs hadn't scheduled, then I'd try to track down the users. And as soon as they'd call me, then I'd look at logs, do a trace job, try to get on the node, look at their script, do everything I could to track down why this thing wasn't working. And then in 2008, I said, well, I got to get better than this. So I created my own little web page just so that the users could see the utilization on our clusters, see what jobs are in there, and give them a little information, how many cores they'd asked for. Well, that created a problem because then I would tell my users, I want to see a queue built up so we have a true load of what we need to, how we can buy resources in the future to meet our demand. Where in the past, most of our users would do a QStat, look how busy it was, and then determine how much to submit or not to submit that day to the cluster, or go to work on their desktop. And so you get those calls saying, oh my goodness, this user submitted 1,000 jobs. I'll never run, and my job's really important. I don't know if you've ever got that issue to deal with, but I have. And they don't understand the queuing system, so they panic. And then I get a lot of calls. So then in 2011, I got a little smarter. Luckily, I'm still getting smarter. And we added a new web page, information, and I created something I call an effective core. How much are you effectively taking out when you submit a job? And then I also put their placement sets, their select statements, and the PBS comments on the web page so our users could troubleshoot that even quicker. And that made it very useful. But also that at the same time frame, Steve Gombashi from Altair came out and sat down with me as we were setting up our new Fission cluster. And I said, what can I do? And he said, have you thought about using hooks? And I said, well, no, what are hooks? And that's when we started thinking about what we could do with hooks. And in 2012, we've now used them to integrate our PBS environment and to handle some of these common issues and reject them at the command line so our users can troubleshoot their own issues themselves. And so that was some of the stuff, and we're going to talk about those hooks and how we've done it now. But also we get these management, they want monthly reports. They want pretty things to pass up the chain. And the big issue is, how many resources are people using? Also, what is the right metrics to use? Is it NCPUs? Is it nodes? Is it memory? How do you properly pass that up the chain? And then also, they want to know it by organization, and they want to know by user, how much each organization's using. How do I roll that up? And then also, then the organization, when they get that, say, wait a minute, who's using it? And they want to drill back down. And so we've had to look into how do we do that. And the last is, how do I compile all the data across from all 4 of my systems to have it in one centralized place? And then one other challenge I didn't put on here, but we'll talk about, is then how do I then properly schedule jobs based on allocation once the departments say, here's what I want to use, or here's what this user can use, or this is what this organization can use. Can you limit them based on that, so then I can then give that out and they have to request resources? Because truth of the matter is, you'll get users from some universities that think they own the system, and they'll completely swamp us. And we don't want them doing that if they're not our key user. But we want to allow them resources allow them resources to solve their problems. So, in my basic understanding of PBS, this is sort of the pipeline where we have places to affect change. So, in the first part, with my job not submitting or scheduling and why, where can we affect that change? So they submit their job, they'll queue their job, they'll schedule their job, then the job gets run and a remove job. And so the user's at the very top, and then they see the output at the very bottom. Hopefully is the pipeline. And so, but with hooks, each one of these arrows between these things are where ideally you can put things in. To my knowledge, this is a prologue or an epilogue. If you want to use it there, there's not a hook, but I hear it's coming. And there, it's limited in what you can do with going between the schedule and the run. But those are some of the things we learned. So these are the opportunities we can affect change. And so these are our problems that we're trying to use. So the job dies immediately. Why? Where can I affect change in this pipeline? And then, what is the effective usage, and how do I do that? And we decided to integrate Gold Allocation Manager. It came out of Pacific Northwest Laboratories. It's an open source software that we've used to integrate and help us answer these questions. So I'll use this chart here on the right to show us where we try to use hooks and where our limitations are in our following slides. So our first one, checking resources and queue limits. Right there after they submit the job, that's where I want to put my hook. That's where I want to affect and check what they've done. And so our problem is we're getting incorrect resource requests, so we're violating our queue limits. And the purpose of this hook right here is to see what the job requests and to cancel it immediately if it would never run on our system. And then also provide feedback to our users so they know what they violated and know where to go. This was one of my first hooks that I did, and it took me about 20 hours to put it all together. Now, I've done Python since '98, and this is the API that they use, or the programming language they use to do hooks. But this was still a challenge for me to understand Python in PBS, and there was a couple issues I ran into. But I called Steve and Scott Campbell at Altair, and they helped me get through that, and I gave them enough feedback, and within couple days we had it working for me, at least that part. There's still some limitations, but it was a lot better. So the issues was, where does PBS hide all their different objects in Python? And then what are the different resource request cases that you would get? And so we did successfully implementing it using hooks, and these are some of the results we get now. So now when the user submits this one, and they even do a capital I, which just hangs, or in batch, now they get this message. You've requested 34 NCPUs, and this is more than available on a Fission Compute node. Here's how you do it. If you need more help, go to our webpage. Now they've solved it. And what was funny, on one of these cases, I had a user submit a job to a different cluster and call me up and say, it's saying I'm on the wrong cluster. But I know I'm on the right cluster. And I said, okay, tell me what machine you're on. And he told me, he goes, wait a minute, user mistake. He wasn't so grumpy with me anymore. So I just said, read the message, that's the machine you're on. The next one, they would submit this 24-hour wall time to our workday queue, which is an 8-hour wall time. Now they get this one. Your job cert request needs to be modified. You've asked for 24 hours, and this exceeds our limit of 8 hours. Please change your wall time or the queue you've submitted to. Now they understand what they have to do. Very simple. This next one here is they've decided they wanted a lot more processors than we allow. Now they get this message instead of just sitting in the queue for the weekend. Your job has requested 1920 CPUs, and the workday queue is limited to 1024. Please make your changes and resubmit. If you can't, contact us, and we'll help you understand what you have to do, or we'll put you in another queue we have available, which is called the approved queue, which is you're approved to run, you're high priority, you can run on the entire system for as long as you want, but we need to know about it. So these are some general things that have helped us get through a lot of the user headache. Very simple, took me about 20 hours, and then another 20 to fine tune it as users called up, or I realized I missed different cases. The next one, calculating effective cores, and I call this eCPUs, something I termed, eCores. They used NCPUs, but I think that's sort of gone out the door since we've started getting multi-cores on a CPU. And so eCores is what I call, and it's effective cores. And the problem I was trying to solve with this is why is my job not running, and how do I do my usage reporting? And so the purpose is to provide a metric for reporting and to facilitate equal access to our different users across our clusters. And we've done that by defining two resources, eCPUs, where I call them INL eCPUs and INL running eCPUs to help me. And we also use these in scheduling and reporting. And they've worked quite well. This one took me about 40 hours to properly determine the logic and get everything set up so I could identify what an eCPU is and how the users were trying to request them in their different select statements. Because PBS does very good at giving you a lot of options, but then you got to figure out what all those options mean. And they'll put plus signs sometimes in their select statements to give you different chunks, and that's created a little challenge in the logic. And then I would use it to test my different scenarios. And was this successful implementing hooks? Well, yes and no. We were able to do it at the submission phase. We were able to calculate their eCPUs fairly accurately. But the problem I ran into is down the road, a job would finish, and I still had them recorded as running eCPUs, and that would affect them in their scheduling. And the only way I had to modify that was to do it at the runtime, but I didn't want to calculate running eCPUs every single time. So what I really needed was also a hook at this point on the server that could go back and tell me and recalculate. This user is no longer running this job, recalculate his eCPUs that are running for effect. Because we tried it with the dynamic resource script, and I just didn't want to do it every time the scheduler fired off. Fortunately, we don't have that many jobs in queue at any given time, but on a big system where you have thousands of jobs, it would be very cumbersome. So yeah, that's where we put it in the end. We did put it as a dynamic resource script, but we'd like it there on a server-side script where we could then do it. And we've had a couple needs, at least in my poor thinking of logic, of how would I want to actually implement hooks at my place, of where I could use it. And I found quite a few needs or uses here at a job completions on the server, not on a MOM. Because the same thing with our nodeless, diskless nodes, when a node goes down, that's all she writes. We lose the MOM, we lose the hook, and that wouldn't work for us. So now when a user submits a job, you can see where the eCPUs become effective. I don't think I have a laser here, or do I? I do, but it doesn't work very well. All right, so this person submitted a job using 6 chunks, 10 NCPUs, 10 MPI procs, and he asked for pretty much the entire memory on the node. And PBS returns, the person's asked for 6 nodes, and he's asked for 60 NCPUs. But you can also see that he asked for all the memory and he asked for exclusive. So in reality, he's locked out 192 cores that no one else can use while his job's running. And he also has 576 cores, three of these other jobs running on our system. So effectively, he's got 576, and if he kicks off another one, he's up there close to 750, 760. And so that's what his true usage is, not just 60 cores. And so that gave us some issues with our reporting, as well as the users looking at my charts and saying, why isn't my job submitting? The cluster's empty. And as you can see, the blue line is really, at the very end, is what all the cores in use. But the green bar at the top is really how many have been locked out on the entire cluster that other users can't use. And so our cluster, instead of saying 1,000 cores is used, we're actually closer to 1,500. And so that became a challenge. But this now eCPUs helps me properly reflect to my users how much of my resources is tied up, and also properly reflect to my management that our cluster is not half utilized, it's really 3/4 because they're going after memory, not processors and cores. So that was quite useful for us. And the last thing is I'd use it in scheduling priority, using a scheduling sort priority. What I would do is I'd say all users have the same access to these queues, but if a user wants to throw 100 jobs in the queue, if he's running jobs and I'm a new user and I submit a job to that queue, I want to be, and I'm not running anything, I want to be able to leapfrog his next job that's queued because he's already using that resource and I'm not. And so what it does is sort of levels the playing field between our users in those queues and allows, so I can have a user submit as many jobs as he needs, another one come in and he'll leapfrog until he exceeds that user, and then he's penalized. And so it works quite well in our environment where we have multiple users. They all think their job's the most important. They're all in the same queue. Who's the most important? Is it the guy who submitted everything first? Or is it the guy who can carry the biggest stick and yell at management and then have them yell at me? So, and then the other thing is then we wanted to be able to have so if everything's equal, then we wanted the biggest job to be the next one in the queue, not the smallest one, because we can backfill around small ones very quickly. But the bigger ones are harder to backfill around. So that's how we applied that one. And then our next one is our management wanted reporting. They've talked about allocations, giving users different allocations, so we decided to integrate Gold Allocation Manager. And the problem is using this is what is the effective usage for an organization, project, or a user for a given time period. And so this thing was, our purpose was to provide management with the information they needed so that we could go out and get bigger clusters down the road, or properly tell them that you say this organization is the most important in HPC, and we can now show you that we've given them the majority of the allocation to that organization, and everybody's happy. Or the group that doesn't get the allocation goes yells at management and says, we need it more important. We're more important, and they duke it out, and then I just get their allocation. I say, okay, you can run now. This one took quite a bit of time to implement. It took us 320 hours, and it was myself and another person and a couple phone calls to Steve and asking him how I do it. And the challenge with this one is setting up the communication with Gold from multiple PBS servers. It's really easy if it's one server. It's very difficult if you have multiple servers because now you got to go over an HTTP. You have to get all the different protocols working properly. You got to understand their weird syntax when you go across HTTP. And so it became a challenge. Then we had to figure out what things we wanted to track and get the database set up properly. The other challenge is PBS doesn't really take user organization information, and if they do, it would be very difficult. I'm saying what organization you're in, work org, your phone numbers, emails. That's not set up to do that, nor should it be, I don't think. But in Gold, they want to know who's the user, what organization, what's their email address, how can I contact them? And so we integrated LDAP into Gold to provide all that user information. So now we can do our organization tracking. And then we were settling on a method to record job usage. Now, do we successfully implement this using hooks? Yes and no again. The green one at the very top is where we provide a user with a quote. It says, you want to run this job for 1 week, this will be X amount of allocation. And then the next one, between scheduling and run jobs, that's where we say, okay, we're going to reserve that much out of your allocation for your job to run. And you have it or don't. If they don't have it, we reject their job and say, you don't have the allocation to run this job. Go get it. Or talk to someone in HPC to run it. But we didn't quite have a way to implement the charge back at the end. And we did the same thing with the mom. We didn't want the mom doing it because we have users that run our systems out of memory, and then that would never be charged back. And so, again, we needed something on the server side when the job finishes to come back and say, okay, you can charge it. So we implemented a cron job that runs every hour, that goes through the PBS accounting logs, finds the job ID, and if it's done, throws it into our gold allocation management system. And it works quite well. Here's some of the results we have. So now we have 4 clusters. How many jobs ran on that month? How many effective CPU years did they use for the different ones? And how many users ran on each one of our systems? Then we break it down by organization. Which org ran the most hours across all 4 clusters? And this also helps us understand which organization is really taking the most advantage of the different clusters, so we make sure that our software is appropriately patched and applied on those clusters, and maybe we don't worry about the other software that they never use on the different clusters. Currently, we try to install all of our software on all of our clusters. But this helps us now see who's really taking advantage of which cluster. Then we even break it down by the orgs on each cluster, which we were talking about there. And finally, we break it down on each user, how many jobs they ran, maximum wall times they were asking for. And this helps me start to see what they're doing and going back in them and saying, maybe you need to try some scaling studies on your jobs. Maybe you need to move to a different cluster. And also, maybe I need to adjust my queue limits based on how people are doing things to open up queues to certain work scope that they're not doing otherwise. So it was quite useful. All this information we have now is using XML and XSL, pulling information out of a gold database. And we run these reports in very short order, and it helps us keep track of everything. And our last thing is, I tried to apply it to, is determining node health. Now, like I was saying, Bright Computing has something out there, Cray has something out there. Our limit is, we buy a computer, we lease it for 3 years, and I can't go back and say, I wish I had a Cray, or I wish I had Bright on my system, or I wish I had something else. I have what I have, and I got to make the best of it. And so the problem here is our jobs keep dying shortly after submission, and where can I affect change? My part is where I thought in the hook is I could affect it right there. Only problem is you don't have that much power in a run hook. And so what we did is run hooks could give me the node list that the job was going to run on. My thought was go out there, run my little node health, my node scripts on there, see what's wrong, see what's not, try to fix it. And if I can't, offline the node, reject it, and have it try to go through the run scheduling again. Well, I can't offline a node because I can't talk to the server because it's running serially. You need to go in parallel. Didn't help me there. So we came up with some other ways to try to do it. In the end, we found we just couldn't do it using a hook, but we had all the scripts in place, so now we have a cron job that runs every 15 minutes. Very limited what we can do because we highly used nodes are constantly getting new jobs submitted, so we can't go in and check and repair those because we don't want to run our scripts on jobs that are our nodes with jobs on them. So we weren't very successful in this one, but we gave it a shot. I'm just trying to understand what I can do with hooks, and that was what this presentation is. So our lessons learned, hooks in general, they take a bit of patience, trying to understand the methodology and their limits. Quite a few calls, reading the documentation. It was new, but it was a very useful tool. I was unable to provide feedback to users when we have planned downtime. They'd submit a job, it'd just go sit in the queue, and they'd never realize that they couldn't submit that job because we were having an outage in 5 days, and they submitted a job for 7 that could actually run in 3 if they properly handled their wall time. So I couldn't give them information without rejecting their job. So that would be a nice feature. And the other thing we talked about, I'm unable to connect to the PBS server from a hook. And so that limits a lot of the things you can do with hooks. But our implementation of hooks did help us in helping our users fix their own issues. It helped us in our reporting usage and scheduling such that now users feel like they're getting equal access, equal resources, equal priority to resources once they submit their job. It's helped us integrate PBS with our environment using Goal Allocation Manager and LDAP. And the last thing, the most important part to me, is I've reduced my volume, my grumpy calls significantly. I probably get 3 phone calls a month now with users who are grumpy, and we continually add new users. We add about 20 new users a month to our group, and we'll probably lose 10 as they get their research projects going on and off. So anyways, that's what I have for you all today. If you have any questions, you can come back and talk to me on break. I'd be happy to answer them. I don't know if I'm allowed to answer your question, Steve.
It's a small group, so let's take one question and.
What now? I can do it now. Well, you could have told me that yesterday. No, I appreciate it, Steve. So anyway, I'm still learning. We haven't gone to 11.3 yet, so I can't do it now. I have to wait till an outage.
All right, one more question, and then go ahead.
Well, one thing you'll learn at national labs and politics is certain users think they have better recognition if they go out and buy their own machines. And so they'll go out there and say, I'm doing a very important project, I have some money, I'm going to go buy my own cluster. And then we have to deal with it. Or some users say, we need lots of memory, or we need the fastest processors because we don't need a lot of them, we just need some fast ones to get my job done because they don't scale very well on the higher clusters. And so we have some Sandy Bridge clusters that we use for licensed-based software, commercial-based software. We only have a limited number of licenses, but they got to run very fast because we don't want them sitting on our slow, big cluster, that doesn't scale well. And so that's why we've done it. So we have big memory, fast processors, and then our general purpose, and then we have our capacity machine, which is our big 12,500. All right.
All right. Thank you very much.